start the time domain technique. What we have done so far through lecture 1 to lecture 3 is representation of control systems in the frequency domain. And in frequency domain, we represented systems by transfer functions, GS or TS, and also by block diagrams and signal flow graphs. Now we are going to represent it in time domain. We want to see how we can represent a control system in a time domain. So if we want to start with a simple example, which is an RL network, we know that this guy can be represented as, if in frequency domain, as G of S, as any output, for example, voltage in the inductor to the voltage in the input in the function as function of S. So this was our representation of the problem in the frequency domain. Now we want to see how we can show this as an alternative representation in the time domain. This system is a first order system because the governing equations are first order. I know that the input voltage is equal to RIT, the voltage in the resistance, plus inductance L di of t to dt. This equation is the ODE that comes from physics of the problem. We call this state equation. So in the concept of time domain, we call the governing equation ODE as state equation. Now, if I, for example, want to solve this problem by Laplace transform, I know that Vs is equal to RIs plus LSIs minus LI0. So I can say that Is as the parameter to be solved is equal to V over R plus Ls plus the initial condition Li0 over R plus Ls. Now, if you want to calculate unit step response, unit step means that V of t is equal to ut, unit step function, and Vs is equal to 1 over s in the Laplace domain. So Is would be 1 over s R plus Ls plus Li0 over R plus Ls. And with partial fraction expansion, I can say that the first guy can be written as these two fractions, and the third remains as it's from lecture 2. So IT would be K1 UT, because 1 over S's inverse Laplace is unit step plus K2 UT e to the power of minus R over LT. This is something we have solved already, plus Li0 UT e to the power of minus R over LT. So this is what we know from previous lectures regarding the time domain solution. And what we want to add here is first the state equation, the terminology state equation, goes to the governing equation of the system, the ODE that we have, and also IT, which is the controlled variable, or we discussed it in the frequency domain as the output of controlled variable, or the second hand of the equation. So in this equation, in this state equation, I know that this guy is input, and I name this IT as state variable. So two terminologies that I'm now learning about solving this problem is state equation and state variable. Clear? Okay. Now in this system, for example, I gave it like output is VL. Okay. So if output, there are so many possibilities, like output be VR or output be VL. If output is VR, I can write it as RIT. So this guy is algebraic equation of some parameters and state variable or input. Also, VL is equal to L di to dt, but can also be written as total V minus VR. Now, what we want to learn here is that this is called output equation, and here this part is also output equation. So depending on what parameter I want to be as output of the system, I want the voltage of the resistor or voltage of the inductor. Depending on that, I can write the output equation. But why not this one is selected? Because I want the output equation to be an algebraic equation, not complicated ODE. So algebraic equations that I can write regarding any parameter in the system is called output equation. The combination of what we showed, state variable plus state equation plus output equation, this is called state space representation. These equations are not always unique, but any representation, any combination that we can write is the state space representation. Clear? Any question? No question? Okay. If you want to go to the general procedure discussion on how we are showing the system as state space representation, we can say we select particular subset of all possible parameters, okay, and we name them state variables. For example, in the previous example, we selected IT as the state variable. Then for an nth order system, the previous example was first order system, We write n simultaneous first-order differential equations. We will discuss how. The previous problem was first order, so we wrote one first order differential equation and we named it as state equation. In step 3, we can solve the problem for any time based on Laplace transform and inverse Laplace transform. This is not part of representation, this is part of solving the problem. Then for 4, we have some algebraic combination of state variables with the system's input to find other parameters. These are called output equations, and the general form of this state variables, a state equation, and output equation is called state space representation. Now let's go to another example to show what is going on. For this system, an RLC network, I know that in the frequency domain, voltage is equal to Ri as function of S plus Ls Is plus 1 over Cs Is. Okay? This equation is not first order and is not two equation. Based on the definitions, here is the system is second order, so I need two number of first order ODEs. In this case, the ODE of this guy is like RIT plus L di to dt plus 1 over C integration of IT dt. So this is not first order equation, this is an integral differential ODE. So what do? I say that I know from physics again, IT is the differentiation of charge, electrical charge with respect to time. So I can write, instead of this guy, I can say V of t is RIT, which is R Q dot. So I is Q dot plus L I dot is L Q double dot plus 1 over C integration of I would be Q. Now I have this two different ODEs, okay? I have two different ODEs. How can I make them two first order equations? If I choose parameter X as I and Q, what do I have here? I can say that X dot, which is I dot and Q dot, is equal to equation 1. I dot is Q double dot, but I don't want second order ODEs. Q double dot comes from the first equation. What is the, I can say Q double dot from equation, which is I dot is equal to V minus RQ dot minus 1 over CQ divided by 1 over L. So I can write it as 1 over L V minus RQ dot minus 1 over CQ, and Q dot is I. So this time terminologies are like this. I have these variables which are state variables. These are two first order ODEs. You see that I don't have double dot, Q double dot, I double dot in the equations. I have just Q dot, I dot at most for the differentiation part. So I chose state variables and I and Q. Clear? Now I want to write output equations. Okay, output equation. For example, if I want the voltage of resistor, it is algebraic equation from parameters and the state variables. Accepted. VL is L di to dt. This is not accepted because it's an ODE. I want it as not ODE but algebraic equation. So I can write it as V total voltage minus voltage in the resistor voltage in the capacitor. This is accepted. And voltage in the capacitor is 1 over C integration of I, or 1 over C Q. This guy is also accepted. I wrote 3 output equations. Here, the important thing we understand is that state variables, so these are output equation, and this guy is output equation. And state variables are linearly independent, I and Q, because they have some differential relation to each other. They are linearly independent. Clear? So if I want to show it much more in standard form, matrix form, I can say, okay, my state equations were LQ double dot plus RQ dot plus 1 over CQ equal to voltage, and I was Q dot. I said that state variables that I'm choosing were X equal to Q and I. So X dot was like I dot. So I dot is Q double dot. Okay. And Q double dot from equation is 1 over voltage minus 1 over CLQ, voltage over L, and minus 1 over RL I, and this guy is Q dot is I dot. So I know that Q dot is I, it comes from here, and I dot is Q double dot. Q double dot comes from this equation, which is Q double dot is V over L minus R over LQ dot minus 1 over CLQ. So I was wrong about this part. R over L. Let me, yes. Then I can say that this Q dot is also I, so I put I here, and this Q is itself. Okay. Now what can I write? I can write that X dot is some matrix as function of X, which is Q and I. This is X. So the first equation is I, so 0, 1 is I. The second equation is minus 1 over CL and minus R over L plus 0 and 1 over L voltage in the time domain. So these equations are in the time domain. And let's say that Y as output is like, let's say, voltage of L I'm just selecting. I could write three different output equation. I'm selecting voltage of the inductor. So voltage of the inductor is like V minus VR minus V of C and V minus VR, which is RI, and V of C is like 1 over CQ. So this is algebraic equation. So I can say V of L is also multiplied by XQI. This is like minus 1 over C. This is like minus R plus some V. This representation is a standard form in the form of x dot equal to AX plus BU. You can see this guy is A, this guy is like B, this is U, that is input of the system. This guy is C, so Y is CX plus DU. Here D is 1 and U is the input. This representation, okay, is called state space representation. And I can also write alternative Y. For example, if I write Y as V of C, it would be 1 over C0 multiplied by X plus 0. This is also another output equation. So what we need is system variables, or like system variables are I, Q, then we have V, and other variables. We choose state variables from them as X that are linearly independent, and we show them by state vector. So X is a state vector, and the state space in the n-dimensional equations, we have n-dimensional space, we change it to n simultaneous first order equations, which is x dot equal to AX plus BU. This guy is state space representation, and then we write the output equations. This is the general definition of modeling in time domain state variables. These parameters have some names, like x is the state vector, x dot is the derivative of the state vector with respect to time, y is the output vector or the output parameters that we want, U is the input or control vector, A is system matrix, B is input matrix, C is output matrix, and D is called feed-forward matrix. Any question so far? No question? Okay, I want to give another example that is much more complicated for electrical networks. This time I want to give the way that we can apply it to any system. Okay, we want to okay, I have here like V of L, V of R, V of C. I have I of L, I of R, I of C. I have input voltage V. How can I choose the state variables? One of the methods that we emphasize here is that select the state variables by writing the derivative equation for all energy storage elements. Energy storage elements are like the VL, the inductor, is like L di of L t with respect to time, and also capacitor V of C is like, we have to write it like C d V of C with respect to time is equal to I of C. Then In these equations, choose the state variables as quantities that are differentiated. So this guy is differentiated, this guy is differentiated. This means that I have to choose x as I of L and V of C. So in order to be able to choose the state variables x much more like with some rules, if we want, in electrical networks, we say we write the energy equations, energy storage elements equations. Here is the inductor and capacitor, which are not like energy dissipators like resistor. Then the variable that is differentiated inside the equation, like here V of C and I of L, are chosen as X. Okay. Second step is applying Kirchhoff's voltage and current laws to obtain other unknowns. These are for other unknowns. What are other unknowns? In these equations, this is unknown for me. This is unknown, not differentiated parameters. So if I want to write that VL, what can I write for VL? I can write that the voltage minus input voltage minus VR, or VR is equal to VC. In terms of other X parameters, so let's keep it here. I will explain next. And the next equation is I of C. I of C is like I of L minus I of R. What should I do next is to look at these equations. V is input, it's okay. VR is not in the X, so I have to write it as some equation in the X. What can I write it? I know that here the voltage is VR. The same voltage here is happening, so I can write it as V minus VR, so VC. So I wrote the equations based on input parameter and X state variables. Here IL is state variable. It is okay. It can remain here. But IR is not inside X. It's extra variable. Instead of IR, I can write V of R over R. But again, V of R is not helping. Instead of V of R, I can write VC. So VC is equal to VR from in this network. So over R. This is X. This is inside X. So the equation is okay. Now I want to combine step 1 and step 2. How? I say the equation 1 is LdI of L with respect to time differentiation is equal to VL. What is VL? Is V minus VC. And the second equation is C dVC to dt is IC, which is IL minus VC over R. So these two equations are the state equations. You will see that I can change them into matrix form. I will change them here, so I keep them here. Then it says, in the fourth step, write output equations. It depends what I choose as output. For example, I can choose I of R as output, so algebraic equation for this is VC over R. Or I can choose I of C as output, the controlled variable. So I can write I of L minus VC over R. Again, in terms of, so these functions should be in terms of X and input, not other parameters. So if X is, how did I write the X? I of L and V of C, I can say that X dot, which is dIL to dt and dVC to dt, is equal to so di to dt is like V. I have like 1 over L V and minus 1 over L VC. Okay, and the second equation is like 1 over CIL, and this guy is like minus 1 over CR VC and 0 from input. Again, this guy is like x dot equal to AX plus BU. And output equation can be written as any of these, like y equal to something multiplied by x. If I write it for example, this equation would be 1 minus 1 over r plus 0 v, that is input. So this is the second part of the equation. These two ticks are state space representation of the system. Any question? No questions so far. Okay, that's good. Let's have 10 minutes of break.